All right, hey everyone. We're looking at dividing radicals, which means rationalizing the denominator. So there's a couple of ideas we want to talk to you about first here, then we'll get started with our examples. There's two types of problems you'll see on the top part of this. All of these are square roots, and so we'll go through simplifying and rationalizing the denominator, and then below that we're looking at other kinds of radicals, so cubed roots and fourth roots, and that's going to be more of the new material, but it's based upon skills we've already seen before, and so we'll get to that in just a moment. But let's start off with something that's probably more basic to the review, and we want to start off with an idea called prime factorization, as that will show up a little bit later on. And so let's just take a look at an example here. Let's say we want to factor 18. So, you know, factors are multipliers. So factors are something times something. And we know we can factor this in several different ways. So let's use 9 times 2 as an example. Now, when we factor it, we usually stop right here. But if we're talking about prime factorization, that means we want to keep going until our factors are prime numbers. 2 is prime, 9 is not, because 9 can still be factored. So let's factor 9 into 3 times 3. However, we're going to format that as 3 squared. So if you have a repeated base, like 3 times 3, we're going to leave it in exponential form. And that'll help us a little further down the page. All right, so that's a skill to keep in mind. Here are some basic rules that we've seen and some new ones that we're going to look at today. Recall that if we have the square root of a times b, so these are the bases, you can treat that as if each base gets its own radical. So this only works with multiplication, right? It does not work with addition, because that would be a binomial. But with multiplication, this works. And that means it works with multiplication. It also works with division. So if we had the square root of a fraction, a over b, well, then we can say the numerator gets its own radical and the denominator does too. Again, this is true forwards and backwards, so we could start off with problems that look like this and then turn it into this. And so that's a skill that we may use from time to time. Here is more of an illustration than a core rule, but let's say you have in the numerator radical a times c and in the denominator radical b times c. So using this concept that we saw earlier, usually we just do this in our heads, but I'll write it down here. We can take that numerator and split that up into root a times root c, and in the bottom we can split that up into root b times root c. And that's very handy when we want to find common factors to reduce. So root c is the common factor. They cancel out, and leaving us with root a over root b. So we'll also be using that technique as well. Some basic steps that we're going to see as we go through this process. First, we want to look to see if we can factor those numbers with the idea of being able to reduce those fractions. If we can reduce, then our values are a lot smaller, and smaller means easier to work with. Once we've checked for any factoring or reducing, then we will rationalize the denominator if we still need to do so. And then once we're done rationalizing the denominator, there's a possibility we might need to check one last time to see if we have any further reducing of the fraction. Usually not, but it's possible, so just check in case. So let's take a look at example number 1. Here we have root 15 over root 12. So step number 1 is to factor. So let's factor that root 15 into 3 times 5, and factor that root 12 into 3 times 4. And we're using this idea here where we can cancel out those common factors. So root 3 over root 3 leaves us with root 5 over root 4. Now, because that's a perfect square, we can take the square root of 4 and turn that into a 2. So what we saw here was just step 1 and 2. We factored, we reduced. We never had to rationalize the denominator at all because the denominator simplified so that we did not have that radical remaining. So we're done there. Let's take a look at problem 2. We have several different steps we could take this. We could actually factor and reduce as a first step. But because this is a perfect square, I guess we could just simplify that right away. So why not do that? Turn that square root of 4 into a 2. So I'm not really factoring, I'm just simplifying. And I do see that we have something that can reduce. Remember, the numerator needs a placeholder of 1 so it does not stay empty. Now let's factor that denominator. So we have the square root of 4 times 5. 4 is a perfect square, so that turns into 2 in front of the root 5. So we factored as much as possible. Now we have remaining this root 5. This is now where we want to rationalize the denominator. So let's multiply top and bottom by root 5. We multiply fractions straight across. So on the numerator, I have a root 5. On the denominator, don't forget the coefficient of 2. That's still there. Root 5 times root 5 is normal 5. So that means we will have a denominator of 10. So final answer is root 5 over 10. Here in problem number 3, I have a root 8. And so you might say, okay, let's go ahead and start rationalizing the denominator by multiplying top and bottom by root 8. Possibly, yeah, you could do that, but you would have to reduce at the very end. And what we're trying to do is see if we can make that value in the denominator's radical as small as possible. In other words, can we factor 8? Yeah, we can. We can turn that into a 4 times 2. So that would mean our top stays the same for a little bit here as we're just reformatting the bottom to try and make it a little bit more user-friendly with smaller values. So there's my 8 that's been factored. We can now simplify this radical 4, which will turn into a normal 2, and that'll be multiplied with the 2 in front. So I'm doing a couple of steps here at once as we're reformatting the denominator. Again, we're taking the square root of 4, which is a 2, multiplying that to the 2 in front, so we have a coefficient of 4 in front, and then we have this factor of 2 in the back, so we still have a root 2. So we just manipulated the denominator so that we have as small of a value as possible. And if we can do that first, then we won't have to check for that reducing step at the end. And usually that takes care of it. So I'm now ready to multiply top and bottom by the root 2. Again, if we can work with smaller values, then our operations are just easier to perform. On the numerator, we have this binomial. So that means we're going to distribute kind of from the backside and multiply the root 2 times these two terms. So we end up with a root 3 times a root 2 is a root 6. And then we have a root, let's see, we have a 3 root 5 times a root 10, so you have a coefficient of positive 3 in front, and a root 5 times a root 2 is a root 10. And then all of that is over. We have a coefficient of 4, and that has to be multiplied by root 2 times root 2 is a normal 2, so that will turn into an 8. So final answer is root 6 plus 3 root 10 all over 8. Now again, we can check to see if we can reduce anything. 6 has factors of 3 times 2, but those are not perfect squares. 10 has factors of 2 times 5, but those are not perfect squares. We don't have even coefficients to be able to factor out an even number with the denominator. So, there's no more reducing, and that's because we took the time earlier on to turn that larger value of 8 into a smaller value of 2 in that way. Now, when we get to an example like number 4, you can see that what's different here is that the denominator has a plus sign. Up to this point, our denominator has only had multiplication as the operation. Now with a plus sign, we have to recall that the division bar acts like a grouping symbol, and that means you cannot just deal with the root 2 by itself, because this is really grouped together. It's a bundle. It's a binomial, so we have to think of both terms at the same time. So when we're setting up our multiplier, we're not using just the root 2, we're using both terms together. We call this the conjugate. And so we keep the same terms, but we change the sign in the middle. So instead of a 5, sorry, that's just a normal 5. Instead of a 5 plus root 2, it's a 5 minus root 2. So again, normal 5 minus root 2. I'm trying to scratch out the radical sign there. And now we're going to distribute this root 5 to the binomial. And that gives us a result of, so we have a root 5 times the integer of 5, so that's 5 root 5. And then root 5 times a negative root 2 is a negative root 10. Now on the bottom we have to FOIL this out because we have a binomial times a binomial. So 5 times 5 gives me 25. The outermost terms is 5 times a negative root 2, so negative 5 root 2. The inside terms is positive times positive, and that's a 5 times a root 2, so positive 5 root 2. And then last times last, positive times negative, and root 2 times root 2 is a normal 2. Now the process of FOILing out with the conjugate leaves us with these middle terms, which are exactly the same values, but they differ by a sign. So when we combine like terms, they cancel out, and now the radical is gone from the denominator. So to just clean it up, the top stays the same, and the bottom is 25 minus 2, which gives us a 23. So now we're ready to take a look at this bottom section here. Before we jump into the problems themselves, there's a core idea that we're going to be using that I need to introduce first. So it's not so much a rule as an example here, but think about this for a moment. If we had a problem like 1 over the 5th root of x, we need to rationalize the denominator, which means we have to set up our multiplier here, and we'll be doing that shortly. But when we have this problem and we're multiplying it by that multiplier here to rationalize the denominator, think about where we're trying to get to. We're trying to get to a point where after multiplying these together, we end up with this pattern. We want the power of 5 to match the index of 5. Right now we just have a power of 1. So we need more power. So when we set up the multiplier, we need to figure out how many powers we need. The reason we want this pattern is so that when the power matches the index, they will cancel out, and all you'll have left with is just the x. That's the final step of rationalizing the denominator. So in order for them to cancel out, we have to determine what this multiplier is going to be to get us to this point. So with the multiplier, we have to match the index. Now previously in our problems you saw up above, they were all square roots, so our multiplier always involved the square root. Now this time the problem involves a 5th root, so our multiplier must match the root, so it's the index of 5. You must match the base, and then we're trying to figure out how many more powers do I need. This is the mystery number. And so when we multiply these together, under the radical you're multiplying this x times this x, you add their exponents, and we know we want a 5. So we're kind of problem solving it backwards. If I want a 5, but I only am starting off with a 1, that means I need 4 more powers. And again, that goes on both the top and the bottom. So when we multiply these together, top times top gives me the 5th root of x to the 4th, and bottom times bottom, so 5th root times 5th root is 5th root, and x times x to the 4th is x to the 5th. That's how we can get those to match. And then once those match, they cancel out, leaving us with just the bottom of x, and the top stays the same with this little mini example. So that's how we're going to rationalize the denominator. So this is a key step. If I need to rationalize, to figure out how many more powers we need so that they total up to a grand total of powers that matches the index. So we'll see that more here in example 6. The way example 5 is set up, this one happens to cancel out much more quickly, but we'll really see this concept here in number 6. We'll get to that in just a moment. So let's take a look at number 5. We have the 5th root of 12 divided by the 4 times the 5th root of negative 4. If you look at just the 12 and the negative 4 as if they were by themselves, you might recognize that they could be divisible, right? So this is sort of the factoring and reducing step, and we can reduce right away. So what we're doing here is we're taking a look at this idea as if we had sort of one giant radical like this. We can reduce that fraction. Now we still have this coefficient of 4 out front, so technically that's in the denominator, so it's a 1/4 of. But this is the property we saw right up here at the top, right, where we can have separate radicals and combine them into one giant radical, so we could work on reducing that fraction. That's essentially what we're doing right here. We're taking the separate radicals and we're looking at one giant radical of the fraction because I'm just recognizing that, hey, 12 is divisible by -4, and so we can do that division. So when we do that, that results in a -3 under the radical. So what we have is the 5th root of -3, and we still have that coefficient of 4 on the bottom, so now it's just an integer of 4 like that. Okay, well, I don't have to rationalize the denominator because there's no radical here anymore. So we're pretty much done. Technically, we can go one step farther and take care of this negative sign. And so we can factor that -3 into a -1 times 3. Right, so always remove the -1 away from the positive value. And you can take a cubed root of -1, a 5th root of -1, a 7th root of -1, a 9th root of -1. As long as that root is an odd number, we can still do that. So that will be a -1. So we'll end up with a negative in front of the 5th root of 3 all over 4. So that's supposed to be a negative sign right there in front of the 5th root of 3. Let's take a look at number 6. Here on number 6, we have the 5th root of 10 over the 5th root of 625. All right, so these numbers are definitely a lot bigger. So we have some work to do here to try and factor and reduce. Our goal is to make them as small as possible. So let's start factoring. We can take that 10 and factor that into 2 times 5. Now with a large number like 625, we don't know our factors. That's okay. We're just using our calculator to guess and check to see what it's divisible by. But here's the key. If it ends in 5, you know it's going to be divisible by 5. So that's what I'm starting off with. I use my calculator. I check to see if it's divisible by 5. And it is. We get 125 as the result. So those are the factors, 125 times 5. Now that we have a common factor of 5, they cancel out. So on the top, we have the 5th root of 2. And on the bottom, we have the 5th root of 125, but don't write that down just yet because we can factor this even further. This factors into 25 times 5. Because again, if it ends in 5, it's divisible by 5. So that's what I'm recognizing there. Now 25 could be factored even further into 5 times 5. So I'm just going to save some space and rewrite this as 5 times 5. Now when you're looking at this, you see that you have 5 times 5 times 5. So that's a perfect cube. 125 is a perfect cube, and if you recognize that right away, you could have factored that into 5 cubed. We're going to reformat this using our prime factorization. So if you have repeated bases, 5 times 5 times 5, put that in exponential form, so 5 cubed. That's what we're doing with our prime factorization. So we saw that at the top when we were factoring 18 as an example. We took that 9 and wrote it in exponential form as 3 squared. That's exactly what we're doing here. We're taking the 5 times 5 times 5 and writing it as 5 cubed. Now again, the goal is to make this bottom number as small as possible. So we started with 625, then it became 125, and we took that 125, and it's still valued at 125, but we're writing it in its prime factorization form so that this number, this base of 5, is as small as possible. That'll make our work a whole lot easier moving forward. So now we're ready to set up the multiplier. So we want to match the index of 5. We have to match the base, which is also 5. And then we have to figure out this number right here. How many more powers do we need? So this is what we were leading off with, right? We know where we want to get to. We want to get to a point where the power of 5 matches the index of 5 so they can cancel out. So the question is, how many more powers do you need based on what you're starting with? So in example 6, we're starting off with 3 powers of 5. That means I need 2 more powers of 5. So top and bottom both need that 2. And that way, when we multiply the denominators together, we get the 5th root of, and the base is 5. So it's 5 cubed times 5 squared. So you add those powers. A power of 3 plus a power of 2 is a power of 5. And they'll match. So they'll cancel out here in a moment. On the top, we have the 5th root of 2 times, and 5 squared is 25. So we'll clean that up here in a moment. Here's the final result. We have 5th root of 50 divided by 5 because the power of 5 cancels out with the index of 5, so the base is all that remains. So that's number 6. Now there's a lot of steps in there, and that's challenging because there's so much detailed work. We're not used to thinking of these large numbers and factoring them and looking for prime factorizations. That's really the key skill, just starting off the problem, getting that base as small as possible. So let's take a look at a couple more problems. I'm going to do both of these down here, starting off with number 7. All right, so again on number 7, we want to see if we can factor and reduce. And if you look at these values under the radical of 4 and 8, you might recognize that they will reduce right away. So you can divide both by 4. So we're removing a common factor of 4 is what we're saying. And that's what we end up with. So let me write this now. We have 3 times the 4th root of 1 over 2 times the 4th root of 2. So the 4th root of 1 is just 1. So the numerator is 3. We're dividing by 2 times the 4th root of 2. This 2 under the radical, well, that's as small as you can make it. You can't make that any smaller by factoring, and it has exactly 1 exponent. So we're ready to set up our multiplier. Match the index of 4. Match the base of 2. And then the question is, how many more powers do we need? So we know the index is 4, so that means we need a total of 4 powers. We're starting off with 1 power. That means we need 3 more powers. So we're setting up our multiplier with this 2 cubed under the radical. So on the top, as we multiply this, we have a coefficient of 3 times the 4th root of, so 2 cubed is 8. We'll go ahead and simplify that. On the bottom, you have this coefficient of 2, and then you're multiplying these together, so you have the 4th root of, there's your base of 2, and when you're multiplying those bases, you add their powers. So 1 power plus 3 powers is a total of 4, and we achieved our goal. The powers matches the index, so they will cancel out. So on the bottom, you have this coefficient of 2, and then when the power of 4 cancels out with the index of 4, you have another 2. That 2 comes from the base, and then we multiply that together. And this is our final result then, with the denominator of 4. All right, so you might try this one here. So pause the video and work it out. Take it as far as you can, and then turn it back on to check the work, and I'll work it out here in just a moment. My first step is to factor. Let's take that 10 and write it as 2 times 5. Let's take that 32 and write that as 2 times 16. And the 2's cancel out. So we have cubed root of 5 on the top. And we have several options on the bottom here. 16 can be factored. So you might think 4 times 4, and each of those can be factored into 2 times 2. So we could go all the way and write this as 2 to the power of 4. That's totally fine. Let me show you a different approach. Because this is a cubed root, and we've been dealing with problems with perfect cubes, I'm thinking maybe we can find a factor that is a perfect cube, and that factor is 8. So let's rewrite that 16 as 8 times 2, because we can take the cubed root of 8 right away. So cubed root of 5 over. The cubed root of 8 is 2, so we have 2 in front of the cubed root of 2. So that factor of 2 is now the only base. So again, the goal is to make this bottom value as small as possible. I can't go any smaller than 2, so we're ready to set up our multiplier. Match the index of 3, match the base of 2, and then we have to figure out how many more powers do I need. The index is 3. That means I need a total of 3 powers. I'm starting off with 1 power right here, so that means I need 2 more powers. So that goes on the top and on the bottom. Let's multiply these together and see what the result is. So cubed root of 5 times cubed root of 2 squared. So that's really a 4. Cubed root of 5 times cubed root of 4 is cubed root of 20. And then on the bottom here, don't forget that coefficient of 2, so you have a 2 in front. And then multiplying these cube roots together, you have cubed root of 2 cubed. How do we know that? Because 2 times 2, you add the powers, so power of 1 plus power of 2 is the power of 3. Now these will cancel out. So you have the coefficient of 2 in front, and then you have just the base of 2 remaining. And then lastly, that turns into a denominator of 4. And there's our final answer.